probability of transmitted sounds. So alpha is PC divided by PER times PT. Now they showed that this alpha is greater than or equal to 1 for pulsed classical light, and alpha equal to 0 for quantum light, because quantum light will not show coincidence, will show anti-coincidence. So it will be 0. Now, of course, all this is done assuming that the detectors have 100% efficiency, but they will not. So there will be some reductions in these quantities due to inefficiency of detection. So they took pulsed thermal light and they kept reducing its intensity by using what are called neutral density filters. Now here is an example of a neutral density filter. A neutral density filter reduces the intensity of all frequencies of light uniformly. It's often used when there's bright sunlight outside. You use neutral density filters, you get lovely clean pictures. So they kept reducing more and more the intensity of the incident pulses, and they recorded that parameter alpha. And they found a uniform result. That is, nothing was changing as the alpha was the same. Here it is 98.7, should be actually 100. That's because of inefficiency of detection. So as you kept decreasing the intensity, you would have expected less and less photons, less and less coincidence counts, resulting finally in anti-coincidence, but you didn't see that at all.
Hello, sorry, Partha, to interrupt. There has been a comment that some of the students are not able to hear the talk. Prashant, there is a comment in the chat box that
I see.
You can hear now, no? Yeah, because, okay, thanks, because there was. Okay, Partha, please continue.
Okay. So, therefore, classical light, even when it is pulsed and its intensity is reduced, does not behave like a single photon. It still it behaves exactly like classical light. That is, there's always amplitude division and no anti-coincidence. Next, they took genuinely single photon states. They produced a couple of, these single photon states are usually produced in pairs. One goes to the left, the other goes to the right. So if you detect a photon going to the left, it might be called the heralded photon. Then you open the window of your coincidence counters for a very brief while, so that the other photon can go and be either reflected or transmitted and be recorded within that window. Because if you keep the window too long, then there will be stray photons coming in and so on. You don't want that. You want that for every detected photon on the left, there is a small time window within which another photon is detected on the right. So they did that. And again, these pairs of single photons, they are produced in bunches. So again, you have to cut down their intensity so that you reduce it to a single photon level. So you use neutral density filters here also. And then when they measured the alpha, they found the following. See, there's a clear decrease to nearly zero. So above this dotted line, you have the classical domain, and below that, you have the quantum domain. Then what they did is, they recombined, they took off the two detectors from after the first beam splitter, combined them with two mirrors on a second beam splitter, then it becomes a Mach-Zehnder interferometer. And then they recorded they detected the photons to see if they saw any interference with the same photons for which they had seen anticoincidence. And these were the results. So there was genuine interference of single photons. If you detect the single photons, you see anticoincidence on a beam splitter. So you see real particle-like behavior. But if you don't want to see that, you combine the two, the reflected and transmitted beam onto the reflected and transmitted beams, you combine on a second beam splitter, and you see interference.
Partha, here there is a question from the audience in the chat box that why is alpha equal to 0 for quantum light? In quantum light, there can be coincidence counts due to wave nature. Would you like to respond to that?
Due to what?
Due to wave nature. The remark in quantum light, there can be coincidence counts due to wave nature. So that is the comment.
Actually, you have to go through the mathematics, which I have skipped here. You can go and look at the original paper where they've shown it. But basically what happens is that even when you see the wave nature is there eventually to give you the interference effect. But here you are not looking at the wave nature, you are looking at whether there is anti-coincidence on a beam splitter. And since the light photons are quanta of light, they are not divisible. Even if they are like waves, the entire wave is either reflected or transmitted. That's the idea. That's why you will not see anything else but strict anti-coincidence.
After the SIC, so photons are quantized modes of field. So single mode propagation is used. So in the mathematical formalism, that's why basically one can work out the quantum optical calculation.
That's right.
And you will
have to write the Hamiltonian as number operator. Okay. So this is an extremely important experiment, an extremely important concept, which I find is usually not well appreciated in the literature. People keep talking about classical light beams with photons in it. Now, of course, classical light is, I mean, it is made up of photons, but you can't see their photon nature, no matter what experiment you do.
So, Partha, here it may be useful to comment that many of the students that historically it is said that the photon nature of light was shown by the photoelectric effect, and Einstein got his Nobel Prize for that, really showing. But that was really misleading because it was later shown that this photoelectric effect can be explained by quantized detection. You assume the matter to be a discrete, means atom, and if you use classical electromagnetic wave and assume the quantized absorption, that suffices to derive the photoelectric effect.
So if you go back to the Rogers the aspect experimental paper, they've actually shown that.
Yes, that the photoelectric. So and also in some quantum optics books and so on. So that is very important fact that The many of the effects which are thought of as showing photon nature of light, they are really showing quantized nature of the interaction between light and matter. So
I believe the same is true of also the Klein-Messina formula.
Okay.
So to see the quantum nature of light, you have to do very special things like use squeezed light or produce genuine, single photon pairs by parametric down conversion, things like that. Otherwise, you don't see any quantum effect.
In fact, here there is a relevant remark made by Moinak Bhattacharya in the chat box, a question that has been asked, which I thought would be relevant to discuss at this stage. He said, what happens if you use matter waves instead of light? Alpha will not be zero. So you can talk about the single electron experiments, in fact, for matter also. Like
I mean, that has been done, that was done long ago by Tonomura. The effect is exactly the same. There's hardly any difference, except that in the case of electrons, they are particles to start with. And as I said, for silver atoms, they are always a stream of particles. But it's only when you have a thing like a field, which is classically a field, like light, then there is a difference. So classical light is not a stream of photons. Right. So now let us spend some time on what are called vortex beams and non-uniform polarization. Usually when we talk about polarized light, we talk about uniform polarization. But let me just show you a few pictures of what are vortex beams. These can be produced nowadays in the lab, and they have angular momentum, and they are described by what are called these Laguerre polynomials. So you have discrete integers. People often say they are multiples of h bar, but I find it very odd. This is classical light. You shouldn't be talking about photons at all. But these are just examples of Laguerre-Gauss polynomials. Now let us look at Maxwell's equations for electric and magnetic field. Both of them satisfy the wave equation. Now consider monochromatic stationary state solutions. That is, the electric field. By the way, polarization is defined only in terms of the electric field, not the magnetic field. So exponent, the spatial part and the time part is all exponential minus I omega t. That is what one means by a stationary state. So that E star dot E is the time independent. Now, for such stationary states, these equations reduce to what is called the Helmholtz equation, where the K is omega over C, omega being the angular frequency. Now, if you look at the plane polarized light, then you will see if Z is the direction of propagation, and you have electric and magnetic fields in the X and Y direction, that at every cross section has uniform polarization. It's the same. As the light propagates, the polarization does not change. This is uniform polarization, and this is the most familiar case to us. But supposing you take this Helmholtz equation and take what is called a Paraxial Approximation, which is a small angle approximation, which fits very well the description of laser beams, which also have very small angle. They diverge to very, very small angle. So you make these approximations like sin theta is theta and tan theta is theta, cos theta is theta, etc., then you get solutions to the electric field, which looks like this. Some amplitude A0 times a unit vector in the x direction plus another amplitude in the y direction times the unit polarization vector in the y direction. And this overall, there is a psi of x, which gives you the which are solutions of the Paraxial equation. The psi of x here, these are solutions of the Paraxial equation. So they are Hermite Gauss polynomials and things like that. So supposing you take a beam of light which is not uniform, which is something like this. You have Ex, but two different amplitudes with them. You have Ey, also two different amplitudes. So this is, and these psi's are Hermite Gauss solutions of the Paraxial equation. And the A's denote a complex amplitude of the field. Now, there's something called the Jones representation of polarization. So if we use the Jones representation, the above can be written actually like this. You have A00 psi 10, and you also have A10 psi 10. Similarly, A01 psi 01 and A11 psi 01. That can be written much more transparently as in the second equation. A00 A10 times psi 10x plus A01 A11 times sin 01x. Now the first form shows that the polarization is non-uniform because the Jones vector varies with the position. The second form shows that the polarization and the spatial modes, they are non-factorizable. And this is precisely what I was talking about earlier. If you take a simple case and put A00 equal to A11 equal to 1 by root 2 and A10 and A01 equal to 0, then you get this. The electric vector is 1 by root 2 times the unit vector in the x direction, polarization in the x direction times psi 10 x plus the polarization in the y direction times psi 01. Now this is what is called a radially polarized beam, in which the beam cross section doesn't have a uniform polarization. Such beams are cylindrically polarized. I'll just show you a picture. I'll come back to it. So here is radial polarization. By choosing the coefficients differently, you can also have azimuthal or spiral polarization. As you can see, here is the cross section of the light beam. The polarization is not uniform at all. It's either radially distributed or azimuthally distributed or in a more complicated way in a spiral. Okay. Now, supposing I write for the unit polarization vector the state 0 polarization, and for y I write 1, and for the space I write 0 space, and for 0, 1 I write 1 space. Then the above, this radially polarized light can be written really like a proper Bell state, 0, 0 plus 1, 1. Which is isomorphic, as I said, mathematically isomorphic to the Bell state of 2 qubits. Hence, the spatial and polarization degrees of freedom can be treated as 2 qubits that are classically entangled. Classical states isomorphic to the other 3 Bell states can also be generated by choosing the parameters appropriate. Now, what is very important to or interesting to note here is that it is clear for all this that there is a four-dimensional Hilbert space. Hilbert space of polarization times the Hilbert space of space, that is propagation. In classical optics, where each polarization is the span of the polarization vector Cx, Q, and it's a two-dimensional polarization Hilbert space, and H space is the span of the solutions of the Paraxial equation. So denotes a two-dimensional Hilbert space. So these are the classical analogs of the quantum of qubits. Okay. Now I come to the next question, which is question of reality, contextuality, and so on.
Partha, there is a question you might like to take here, this stage. Nilnath Kundu, why is there no Psi 00 and Psi 11? Nilkanthi, can you please explain the way you have written? It's not clear. Hello?
Yeah, so basically I'm asking that in the solution of this psi function, there is only psi 10 and psi 01. Why is there no, because ij belongs to 01.
Which psi? Where is it written? Which?
In the expression for the electric field. So it is a linear combination of psi 10 and psi 01. So why is there no psi 00 and psi 11?
This is just one example I have given. I have given one example so that from that I can deduce the radial polarization. Okay, this doesn't mean this is the only thing you can write down.
So here you are assuming no contributions from those.
Yes. This is just an example.
This is
a particular kind of non-uniform polarized light.
Non-uniform, so the E's are not the same in that plane, the small e vectors. That means
you have Ex as well as Ey with different coefficients. So that the polarization varies from point to point.
And so this Ex is on the X plane, the X plane thing. Normal
X here is X, Y, Z. Sorry,
Z.
This E bracket X, that X is the vector X.
E bracket X is
I should have said right at the beginning.
Okay.
When I defined the here, X and E as a function of X and T, where X is X, Y, Z.
Z.
Okay. I did not use that arrow on the top because it's correct.
So that means when you
T is separated, so that's only the spatial part.
So the non-uniformity is the variation of that thing, the different amplitudes of Ex and Ey.
Yeah, so you can see that very clearly in these pictures, how the polarization varies in the same transverse plane to light. It's not just one polarization, several polarizations. And if you go to this, if you go to these, then as you go from one to the other, the polarization will keep changing. And that gives you what is called the angular momentum of light, classical light.
Okay. So, and here I think that is another important point that may be useful to stress, that when you go to the entangled description, you are discretizing. That step is the crucial thing, but the way you are discretizing the Ex and Ey by putting them as 0 and 1 qubits. You come to
No,
that
that is
slide.
just a notation because
No, it is more than a
Hilbert
notation
space.
because it is where you are. It is really a continuum that you are discretizing it by considering these two as two distinct qubits.
It is because because
and
polarization,
like the way in the Stern-Gerlach case, it is a continuous position space, but we write it in that notation. Notation means here you are viewing that continuum as something discrete. So we are discretizing it in that way and having an equivalent and entanglement.
Well, you see, the polarization vector is the direction of the electric field.
Yes.
So that always picks up a particular direction for polarized light.
Yes.
So that's what we mean here. So if it is in the
so if the directions are in the X plane, you denote by that state. This means here 0. Just like in the Stern-Gerlach case, you have all the position states in the upper half of the plane. These are all different positions. So it's a continuous function there. But you label it as one spatial qubit. So, and we will write it as an entangled, spatial spin entangled. So for this is a useful jump for the students to remember that this is a non-trivial step.
Okay, so now in the classical case, of course, there is no question of either I mean, realism is assumed, locality is assumed. However, contextuality is something that comes in a very deep way, and this is what I would like to just spend a little time on. So there is a no non-locality in these intra-system cases of but there is contextuality. How? See, what do you mean by contextuality and non-contextuality? Usually in classical physics, people say that all classical systems are such that they are non-contextual. That is, the values of what you measure are already predetermined. So your measurements simply reveal those values. And if there is a system with 2 degrees of freedom, like in the case of light, you have the spatial propagation degree of freedom and the polarization degree of freedom. If you measure one, then the other is not affected. So this is the meaning of non-contextuality. Now, if you take a state like the one here, 0, 0 plus 0, 1 plus 1, 0 plus 1, 1, this is a completely separable state. This is not a entangled state. And one can show that here, the measurement of one variable will not affect the measurement of the other variable, because they belong to 2 different orthogonal Hilbert spaces, and measurement of one does not affect the other. On the basis of this, I'm not going into the details now. The details can be found in some papers. You can derive what an inequality which is exactly has mathematically the same form as the CHSH, Bell CHSH inequality. On the other hand, if you take something like this state which is radially polarized, then one can show that this violates that inequality, just as in the quantum case, exactly by the same factor 2√2. Now, this is surprising and shows that contextuality occurs in classical physics as well, and is therefore an aspect of classical reality. Now, this I find is a very important point. I made this point long ago in a paper where you can find the deduction of the CHSH inequality. This has been reduced by other people also. There are lots of papers in Physical Review and other optics journals. You can look them up. So contextuality is violated in classical optics Now, this is something very, very important. Normally, when we talk about classical physics, we tacitly assume that we are talking about Newtonian, Hamiltonian classical mechanics. There, of course, there is no question of any superposition there. Therefore, no interference, no entanglement. But there is this whole branch of classical physics, which is optics, quantum optics. There you have interference, you have entanglement, you have violation of the CHSH type of inequality. So mathematically, the two are the same because both are nothing but Hilbert space representations of reality, of physics. And as long as you have a linear vector space with an inner product and so on, you will get the same mathematical result. The physical interpretation may be a bit different. That's a different point. So here I come to a very important conclusion, which is that the requirement of non-contextuality as an inherent aspect of classical realism is untenable. But this is what is usually assumed in all hidden variable theories. Hidden variables are supposed to be non-contextual. But if you look at quantum mechanics as such, let us see what happens. So now let's come to the most famous entangled state, the EPR state. You have two systems, A and B, which interacted in the past and have now separated. So you have two spatially separated, mind you, spatially separated and non-interacting EPR pair. Since there is no interaction between them, no matter what you do to A cannot affect B. No matter how long you wait. People talk about within the light cone and so on. All that is not necessary. That is necessary only when you do an experiment to make sure that stray influences do not affect your system. But conceptually, it's very clear. All you need is spatial separation, and that is what Einstein said, spatial separation, and the fact that they are not interacting anymore. So nothing can go from one to the other. Now, the original EPR paper was a long paper with lots of discussions of what is reality, what is locality, and so on. Einstein was not very happy with it. Actually, it is said that it was written by Podolsky, and Einstein dissociated himself from that later on in life, and in several letters and also in his autobiography, he has written clearly what he meant by that problem, what he meant by incompleteness. Now, let me just go through it. The argument is extremely simple and very easily understandable. So let us look at the EPR state. Psi of AB is 1 by root 2 psi A plus psi B plus psi A minus psi B minus, where by A plus A minus and B plus B minus, I mean two orthogonal states of A and B. So here is an entangled state. Now supposing we measure A plus on the left side, system A, we measure A plus. We find A plus. Then we can immediately say that B is in the state B plus. But we could have also measured something which is incompatible with the first one, namely A minus. And then we would have found the state B to be in the B minus state. Now Einstein makes this very crucial assumption he makes a reality and locality assumption. He says the factual, real the factual, that is real, situation of B cannot depend on what is measured on A. And he says, on this we must hold fast. There is no way we can give this up. So that is the case. Then we've just seen that quantum mechanics assigns two different wave functions to the same state B. So therefore, quantum mechanics is incomplete. That's it. That is the entire argument. Quantum mechanics says that B will have two different states depending on what I measure on A. But the factual situation of B cannot depend on what I do on A. Therefore, quantum mechanics is giving us two different wave functions for the same factual state. This is what Einstein meant by incompleteness. However, most physicists concluded from this that quantum mechanics is non-local. And this was further.
So Partha, you have 10 minutes more.
Okay. Yeah, I have nearly finished. So most physicists concluded that quantum mechanics is non-local, and this was reinforced by Bell using local and non-contextual hidden variables, not quantum mechanics as such. Let's look at what Bose said. Bose had a different take altogether. Bose wrote in his paper, of course, there is in this case, like that, just consider no question of any mechanical disturbance of the system under investigation during the last critical stage of the measuring device. These pictures are interfering with.
So you can read it out. Yeah.
No, I can't see it either.
Okay.
There is, in this case, like that, just consider no question of a mechanical disturbance of the system, etc. But even at this stage, there is essentially the question of an influence on the very conditions which define the possible types of predictions regarding the future behavior of the system. Then in the abstract he wrote, in this connection, a viewpoint term complementarity is explained from which quantum mechanical description of physical phenomena would seem to fulfill within its scope all rational demands of completeness. Now, here is Bose is arguing that quantum mechanics is not incomplete, as Einstein is insisting, because Einstein is forgetting the fact that there is contextuality, and depending on contextuality, quantum mechanics predicts a different state. So if I have changed my apparatus, I'm measuring something different, my system has changed. That's in the very nature of quantum mechanics. And therefore, if you take that into account, then the two together gives you completeness. So this was Niels Bohr's attitude. And I personally, these days, so let me finally say this, that you have contextuality, complementarity, and completeness. So complementarity and contextuality are intimately connected, and the conventional notion that a physical property must be independent of the context in which it is measured is not supported by empirical evidence. Let me end by saying that in this connection, reading philosophy is very important. And I have always been very much interested in philosophy, particularly Indian philosophy. And there are systems in Indian philosophy, particularly a Jaina system called the Syadvada, which is multi-valued. Now, the problem with a lot of these things is sticking to the Aristotelian bi-valued, two-valued logic. You do not, the middle is excluded. It's either yes or no, true or false. But this is not how things are really in nature, even in the classical world of ordinary things. For example, I'll just give you one example. Supposing you have a clay pot. Now it is black when it's not baked. It is red when it is baked. But if you ask the question, what is this color when it is being baked? There's no answer. But it's a legitimate question. And so you use what is called multi-valued logic. And people have now shown that this China system is what is called in modern terms paraconsistent logic. That is, they always say syad, if this, then that. So that is much weaker statement than under all conditions, this is this or that. So this is why it's called paraconsistent logic. If you follow paraconsistent logic, then there's this famous story of the 7 blind men who had never seen an elephant. And they go to see an elephant, and each one touches a different part of the elephant, and then they start quarreling about the nature of it. So the idea is that elephant has to be, or everything has to be seen from 7 different points of view. It's a 3-valued logic, so 2 to the power 3 minus 1 is 7. So there are 7 combinations. It's called Saptabhanginaya. As you look at it from that point of view, then you will see contextuality and how all these things have to come together for completeness. What Niels Bohr did is just a small part of that wider system of philosophy. Thank you very much.
Thank you, Partha, for this very stimulating talk. And as usual, with Partha's talks, wonderfully lucid. So I'm sure students must be motivated to ask questions. And students, please, and others, please feel free to ask questions. I know Partha loves to interact and answer questions. So there is a person, Kishore. Kishore, you please unmute yourself and ask the question. You have raised hand. Kishore Kalita. You have raised hand. You have a question to ask? No, he's not asking. So, Nilkant Kundu makes a comment that very interesting talk. Before I never heard of classical entanglement. So, Partha, would you like to respond?
Yeah, I mean, now, when we started way back in 2001, I still remember when I gave the first talk in the SN Bose Center, I was shouted down. But then things have developed, and now I wish I could give you a complete list of references, which maybe later on I can send you. And there are lots and lots of papers. The whole group's now working on this, and this has a promise for also quantum information processing. So what you need is information processing. So, and classical light is stable. It's stable in the sense the entanglement is stable. There is no decoherence. So people have started using these things.
In fact, here I may make a comment that there has been a very interesting paper in Optica showing the application of classical entanglement in high-speed kinematic sensing, so that any of the students may try to look up. This is an area in particular here, and a particularly a review paper in Reports and Progress in Physics in 2020 that is very relevant, which summarizes the status.
Yes.
But also I may Partha add that if you may look at, there is an instructive paper in NPGA Quantum Information 2019, where they've revisited the issue of how, to what extent non-contextuality, this connection between classical entanglement and non-contextuality. That is a very, very critical perceptive discussion where they raise some very subtle questions. That is an NPJ Quantum Information, volume 5.
Can you send a copy to me?
Yes. It is the Marquez et al. I will send you the reference and maybe.
Okay.
I will send you the reference.
Yeah, if you can send to us also, we will put it here.
Prashant, I have a problem here in downloading because I'm not going to institute these days.
Okay.
This is NPJ Quantum Information, volume 5, page 5, 2019 paper.
Okay, I'll do it.
Because this raises some deep questions about.
And how about that Optica?
Optica paper is a bit dated, but it will be useful to look at that review paper, Reports in Progress in Physics, volume 83, 064001, 2020. So you may please send the papers to Partha and to me. I have that paper, and the kinematic sensing paper is Optica 2864, 2015. But there may be more studies on this. I have heard high-speed kinematic sensing.
Can you repeat again? 2015.
That Optica paper is volume 2, page 864, 2015.
Okay.
And there may be other studies following this. So I had been following this because some of my students have been studying this topic. So I thought to mention this. So you may be interested also, Prashant, to look at it because you have been doing.
Also, please look up Eberle's paper. He has some beautiful papers on these questions of how classical entanglement can be useful. Eberle and Kian.
Yes.
Well, any other questions or comments?
Oh, okay. There is a comment made by Kalipada Chatterjee. Can you say Kalipada?
Yeah, Kalipada, just tell that reference again. I will download and share with everybody.
Kalipada?
Yes, sir. Sir, I found out the paper on classically entangled optical beams for high-speed kinematic sensing, which you suggested just now. So I've sent its reference and the title of the paper.
Okay.
So my question was related to has the entanglement in classical mechanics been experimentally tested? But now, since I've got the paper, I will go through it, sir.
And there is also one subtlety. See, if you look at Schrödinger's 1935 paper on the entanglement, the current status of quantum mechanics, he spends a lot of time on the measurement problem. Now, the measurement interaction entangles the system with the apparatus. And then the measurement somehow has to disentangle. And the usual concept of measurement is that there is a projection, the von Neumann projection. So Schrödinger already mentions that when this projection, von Neumann projection happens, the unitary Schrödinger evolution stands still. This, conceptually, this is very, very murky. So these days, people don't want to talk about these projections and non-locality. And the epitome of all that is, I find, quantum Bayesian cubism, where they look at everything as updating, Bayesian updating happening. So the wave function is really something epistemic, not something real and out there. Anyway, these are so many aspects of it. And the other point I want to make about this measurement thing is that in the measurement, the entanglement produced by the measurement interaction is also local. The non-locality comes only in the EPR case. And there also it can be interpreted as non-contextual, a contextuality, not non-locality, as Bose said.
And Nilkantha Kundu has also mentioned this paper, class quantum entanglement. Nilkantha, you say aloud?
Yeah, so I shared one YouTube lecture where I think similar to this lecture, it is quantum entanglement and its classical cousin. So I think this is by Professor Eberle, which Professor Partha mentioned. So maybe this is also interesting.
He writes very clearly. And he has a paper where he's shown that unpolarized light is actually maximal entanglement, because the polarization and the propagation are completely entangled, and so that is why you don't see polarization. If you want to see polarization, then you have to break that entanglement, and the degree of polarization is associated with the degree of entanglement.
The non-uniformity of polarization. You mean that?
Yeah, polarization and propagation are so intimately entangled, maximally entangled, that you cannot see polarization in that light at all. That is what is in unpolarized light.
Yeah.
And the degree of polarization that you see in light, which you can produce through filters and so on, will be related to how much of this entanglement you are breaking.
That makes sense.
Very nice ideas. Physically, they are very attractive.
And there is yes, and there have been applications, as that Reports in Progress in Physics review paper discusses, that were altering the spatial profile of the web packet, the change of polarization that occurs. That has been used for some application. So that will be also useful to note from that review paper I mentioned in Reports in Progress in Physics, because by altering spatial profile, that you can change the polarization. It has some important consequence.
Let me tell you a startling experience I had. I was working on these ideas together with R.P. Singh of Ahmedabad, PRL Ahmedabad. So once I went there and I said, why don't you test contextuality? He said, we have tested it. I can show you on the desktop. I said, how? So he produced those, let me show you. Yes, so he produced this kind of light and projected it on the wall from the table. And then he took some polarizers and started putting the polarizer in the path of the beam and changing the polarization at the axis. You could see the shape was changing on the wall. It is so simple. And I can never forget that wonder I had.
Yes, because that is the implication. So it has many applications now. It has, which have been discussed in recent years.
So thank you, Partha Ghose.
Yes, I think we have already taken much time. So
okay.
Hello.
Okay.
Hello.
Okay, thank you.
Hello.
Thank you.
Thank you.
Hello.
Yeah, you want to say something?
Yes, sir. Sir, I have one question.
Can you send that by email, because
yes, because already we have taken a longer time.
Yeah, please send us. You can send me also. I'll forward it to you.
Okay, sir.